Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 11 of Algebraic Topology. Our today's topic of discussion is Simplicial homology. So as I said earlier that our aim is to associate topological spaces with algebraic structures, and in that direction we have already done fundamental group, but for higher dimensions the fundamental group fails to differentiate between two different topological spaces. So for example, we have seen the example of n spheres. So when n is greater than or equal to 2, the fundamental group pi 1 of Sn is 0 for all these values. In other words, if I take S2 and S10, then the fundamental group can't differentiate between these two objects or these two topological spaces. So we need another tool. So we can define higher homotopy groups, but the disadvantage with the higher homotopy group is that they are extremely complicated to calculate. So as a equivalent to that higher homotopy groups, we are trying to calculate the homology. So in general, we calculate homology for general objects, and we will see in the future lectures, but the point is we are trying to see the calculations of homology for these simple objects called simplicial complexes, and so we will be calculating the simplicial homology. Simplicial homology is relatively simple to calculate, and that's why it has very real life applications, for example in image analysis, in data analysis and other areas of science. So starting from a basic definition of dimension of a simplicial complex, it is defined as the dimension maximum or the supremum of all the simplices contained in this simplicial complex K. So of course if we have a Q simplex which is generated by E0 up to EQ, then it has dimension Q. Similarly, let's consider another simplicial complex. So these are the vertices, this is a line, this is a point. Okay, so 0 simplex, 1 simplex and a 2 simplex. Okay, so this is a simplicial complex. We can see that it satisfies the definition of simplicial complex. So for example, if I take the intersection of any two simplices contained in this simplicial complex, then its intersection is also contained in this simplicial complex. So we have a 2 simplex, we have a 1 simplex and we have a 0 simplex. Okay, so according to this definition, the dimension of this K is equal to the supremum of the dimension of S. So supremum, so what about the dimension of this? It is 2, dimension of this is 1 and dimension of this is 0. So the supremum of this is 2. So we can say that it is a simplicial complex and the dimension of this simplicial complex is 2. Invariance of dimension. If we have two simplicial complexes and if there exists a homeomorphism from mod K to mod L, so this mod K is basically the underlying space of that simplicial complex. So for example, if I have a triangle with these vertices, okay, so consider this as a hollow triangle. So in other words, this is a union of one simplex, one simplex, one simplex, one simplex and one simplex. Okay, so 1, 2, 3, 4, 5. So it is basically composed of, it is a simplicial complex composed of 5 1 simplices. Similarly, consider another triangle, so with these 3 vertices. So now we have 1 1 1, so we have 3 1 simplices. Okay, but both of them have the same underlying space. So for example, if this is K2 and this is K1, then the underlying space of K1 is equal to the underlying space of K2, and both of them are triangles. Okay, so that's what it means by the underlying space. So if we have a homeomorphism from the underlying space of the simplicial complex K to the underlying space of the simplicial complex L, then the dimension of L and the dimension of K, they must be equal. Let K and L be simplicial complexes. A simplicial map phi from K to L is a function taking vertices of K to the vertices of L, such that whenever we have a simplex inside K, then its images span a simplex in L. So the repetition, of course, is allowed in the vertices. So our next result is a theorem. If K, this calligraphic K, consists of all simplicial complexes and all simplicial maps with usual composition, then this calligraphic K is a category, and the underlying defines a functor from this K to the category of topological spaces. Okay, so the first thing we have said in this result, that we have a category of simplicial complexes. So in this category, what are the objects? So the objects are simplicial complex. And what are the maps? So the morphisms are basically just the simplicial maps. Okay, so that's the definition of the simplicial map. So we have a category, and the composition, the third important ingredient of the category, is just the usual composition. Now there is a functor. Okay, so we have a functor from the category of simplicial complexes to the category of topological spaces. Okay, so how this functor is defined? So given any simplicial complex, we are taking its underlying space. So given any object of this category K, which means given any simplicial complex, its image under this functor is the underlying space, which is of course a topological space, because it is a subset of the Euclidean space. So it is a subspace of the Euclidean space, which is a topological space. And similarly, given any map, given any simplicial map between two simplicial complexes, we can define this map from, okay, so let's say we have a map phi from this simplicial complex K to simplicial complex L, then we can define the image of this map under this functor, and it's a map between the underlying space of K to the underlying space of L. Okay, so that's how this functor is defined. Our next definition is a simplicial map between two simplicial complexes. So given two simplicial complexes K and L, then we can define a simplicial map between these two complexes as a map phi from the vertices of K to the vertices of L, such that, so this map takes vertices of K to the vertices of L, such that whenever we have a set of points which spans a simplex inside K, then its image should also be a simplex inside L. So under this condition, we define a simplicial map. So the repetition, of course, of the vertices is allowed. If K consists of all simplicial complexes and all simplicial maps, then this makes this K into a category. So in this category, what are the objects of this category K? So the objects of this category K are simplicial complexes. And what about the morphisms? So the morphisms in this category are basically simplicial maps. Okay, so F such that F from K to L is a simplicial map. And what's the third ingredient needed in the category? Of course, it's the composition, and we define composition as the usual composition. So under with these ingredients, this K is a category. Now we can define a functor from the category of simplicial complexes to top the category of topological spaces. So how we define this category? So we take any object of this category of simplicial complexes, and we define its image to be the underlying space. Similarly, if we have a map, a simplicial map between two simplicial complexes, then we define phi in the following way. Okay, so given any simplex S belongs to K, then we take the image of S under this phi mod. So basically this is equal to Fs. So basically the image of S under this Fs. So what is Fs? So Fs is basically a map from S to the underlying space of L. Okay, so taking this S to L. So in other words, what we are just saying is take a simplicial complex in K. Of course, K is a simplicial complex, so it is composed of many simplicial complexes. So take any simplicial complex and take its image under this Fs, and where Fs is nothing but restriction of phi to the vertices of S. Okay, so phi is a simplicial map between K and L, so we can restrict phi to the vertices of S. So when we restrict that, then we get a map. We get a map from S to L, and we can define a map from S to the underlying space of L. So that is the image of S under this map phi mod. And similarly, since K is composed of many simplicial complexes, so we can find image of each and every simplicial complex in this way, and it will give us the image of K under. So basically it will give me the image of the underlying space of K to the underlying space of L. So with these operations, this is a functor, and I just gave you an outline of the proof, how to show that this is a category K of simplicial complexes, and similarly how to show that this function from the category of simplicial complexes to the category of topological spaces is a functor. Okay, so I'm leaving the details as an exercise for you. So an oriented simplicial complex K is a simplicial complex and a partial order on vertices of K, whose restriction to the vertices of any simplex in K is a linear order. Okay, so that's how we define an oriented simplicial complex. So every linear order of vertices of K makes K into an oriented simplicial complex. Okay, so we will see many more examples of oriented simplicial complexes in our future discussions. Now in our first lecture we reviewed group theory, and in this lecture we are going to use some parts of it. So for example, we will see what is a free abelian group. So a free abelian group is the quotient of a free group with its commutator subgroup. So for example, a Z cross Z cross Z up to so on, let's say there are m copies of Z, then it is a free abelian group of rank m. Similarly, we know what is a finite presentation of a group. So finite presentation of a group is basically a collection of generators A, B, C up to so on, and relations. Okay, so these ABC are generators, and these are the relations, and if these are finite, then this is finite presentation. Okay, so the symmetric group S3 has finite presentation. Okay, so there are 2 and 3 relations. Okay, so we can say that it is a finite presentation. Okay, so we can easily write the elements of S3 as well. So what are the elements? 1 x y y square xy xy square. Okay, so of course you can say that why I'm, for example, not writing down x raised to power 4 and y raised to power, let's say, 6. So x raised to power 4, y raised to power 6 is basically equal to, so since x square is 1, so x raised to power 4 is 1, and y 6, so basically equal to y3 square, y3 is 1, so it is basically 1. So since this is equal to x square y3 square, so that's why this is equal to 1. Similarly, if I consider, let's say, x3 y raised to power 5, then this is equal to x square into x y3 into y, so which is equal to, so x square is 1, so this becomes 1. Similarly, y cube is 1, so this becomes 1, and this becomes xy. Similarly, I can take x, y, x. Okay, so this is another word. This is another word in x and y. This is also an element of this group, but if you just play with these relations, then you will see that this is one of these 6 elements. So this is the finite presentation of a group. So our aim is to define simplicial homology for the underlying space of K, where K is any simplicial complex. But we shall first define simplicial homology of oriented simplicial complexes. So let's see how to define simplicial homology of oriented simplicial complexes. So our next definition is important towards calculating the homology groups. So if K is oriented simplicial complex and Q is greater than or equal to 0, and let CQK be the abelian group having the following presentation. Okay, so remember, we have already seen what is finite presentation of a group. So we are going to define a group, and it is going to be a abelian group, and it has the following generators. So the generators are going to be all Q plus 1 tuples with Pi belongs to vertices of K, such that this set spans a simplex in K. Okay, and what are the relations? So the relations are, this is equal to 0 if some vertex is repeated. Secondly, this P0 P1 up to PQ is equal to a signature of pi and multiplied by P pi of 0, P pi of 1 up to P pi of Q. So in short, we can also write it down as pi 0, pi 1, pi Q. Okay, so if we have any permutation of these vertices P0, P1, PQ, then this is equal to the signature of pi. So what is this signature of this pi? So is used to check whether the permutation is even or odd. If it is even, then this is +1. If it is odd, then this is -1. So how to actually calculate that the permutation is even or odd? So we can write down every permutation can be decomposed as product of transpositions. Okay, so for example, if we have a permutation 1, 2, 3, 4, so it can be written as 1 into 2, 2, 3, and 3, 4. So there are odd number of transpositions in the decomposition of this permutation, so that's why this is a odd permutation. So the signature of this is going to be -1. Similarly, we can calculate evenness or oddness of other permutations as well. So that's how we define this CQK. Okay, so it has the following generators and the following relations. So we denote the elements of CQK corresponding to these vertices by this. Let K be an oriented simplicial complex of dimension m, then CQK is free abelian group with bases all symbols, where P0, P1 up to Pk spans a Q simplex in K, and P0 is less than P1 up to so on. So this is an orientation on Pi's. So moreover, this element is equal to signature of pi times P0, P1 up to Pq. And also, most importantly, if Q is greater than M, and what is M? The dimension of K. Okay, so if we have Q greater than the dimension of the simplicial complex K, then all these CK are 0. Okay, so in other words, we have seen an equivalent criteria to define these abelian groups. So basically it says that it is a free abelian group generated by all symbols of this form, which so these symbols generate a Q simplex. So our next lemma is an equivalent criteria of these free abelian groups. So it says that instead of taking all these generators and relations, so it gives a very simple criteria. So it says that this is a free abelian group with bases all these Q simplices inside K. Okay, so if you have a simplicial complex, so let's say we have this following simplicial complex, so something like this, and there's another triangle. Okay, so all of these are vertices. So let's say this is L1, L2, L3. Okay, so so this is a simplicial complex K. So if I want to talk about what is C2 of K, okay, so C2 of K is basically a free abelian group with bases all symbols of this form, where this is a Q simplex in K. In other words, it says that if I want to take, or if I take Q is equal to 2, then basically this is a free abelian group with generators L1, L2 and L3. Okay, so these are all, this will give me all 2 simplices which are contained in K. Now, of course, if this is the vertex, for example, this is V1, V2, V3, and this is W1, W2, W3, this is alpha 1, alpha 2, alpha 3. So if, for example, I take V1, W1, W2, okay, so this in principle this generates a 2 simplex, but then that 2 simplex is not contained in K. So that's the important condition. So consider this Q simplex, so where this spans a Q simplex in K. Okay, so if it is not in K, then we will not consider it. So it must be a Q simplex inside K. So in this particular example, we have 2 simplices inside this K, L1, L2, L3. So C2 of K is a free abelian group with bases all symbols of the form. So in other words, what will be the elements of this C2 of K? So the elements of this C2 of K will be, so let's say beta 1 L1 plus beta 2 L2 plus beta 3 L3, where beta I belongs to integers. Okay, so that's our description of C2 of K, and this is isomorphic to Z3 because it's a free abelian group of rank 3. Okay, so we have seen the definition of the rank of a free abelian group. Let K be a simplicial complex, and let sigma 1, sigma 2, sigma n be oriented Q simplices in K, and these are the only, okay, be the only be the only oriented q simplices in K, then CQ of K is equal to, so n1 sigma 1 plus n2 sigma 2 up to n and sigma n, and where all these ni's belongs to Z, and this is isomorphic to Zn. Okay, so that's how we define CQ of K. So going back to our previous example, if I for example want to calculate what is C1 of K, okay, now of course there are many 1 simplices contained in K. So starting from this gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6, gamma 7, gamma 8, gamma 9, gamma 10, gamma 11. Okay, so this must be isomorphic to Z11. So it's a free abelian group of rank 11 because there are 11 1 simplices contained in this simplicial complex K. If sigma bar is some q simplex with the ordering reversed, then sigma bar is equal to minus sigma. So we can easily see it from the definition. So our next result is important in the direction of calculating homology. So we are going to define the boundary operator. Okay, so consider this free abelian group CQK, and we can define a map which is the boundary map from CQK to CQ minus K. So we defined it in 2 steps. So in the first step we defined the image of any q simplex of CQK, and in the second step we will extend it to the whole of CQK by linearity. So what is this expression? So given any q simplex, so we define its boundary. So we have already seen that how to define the boundary. So for example, if we have a triangle which is a 2 simplex, so with vertices E0, E1, E2, then we can say that C2, of course it's a 2 simplex, so it must be an element of C2 of K. Okay, so we can define this map, and we define the image of this E0, E1, E2 in the following way. So this is equal to, so when we delete this E0, minus 1 is to power 0, so basically it becomes E1, E2, and then when we delete this 1, so we get minus E0, E2 and plus E0, E1. Okay, so this is basically E1, E2 minus E0, E2 plus E0, E1. So basically a special plus minus sum of 1 simplices. So of course an element of C1 of K, because every element of C1 of K is basically of the form, so some integer multiplied by some 1 simplex. So in this case the integer is 1, in this case the integer is minus 1, in this case the integer is 1. So in general the elements of C1 of K are basically A1, E1, E2 plus A2, E0, E2 plus A3, E0, E1, where these AI's belongs to integers. So that's how we defined C1 of K. Okay, so this boundary operator partial 2, when applied on this, give me this element of C1 of K. Now in this way I can define the image of any q simplex, but then CQK is not just one q simplex or the collection of q simplices. Okay, it is basically a free abelian group generated by the q simplices. So free abelian group has elements of this form. So for example C1 of K, in the case of C1 of K we have already seen that this is a free abelian group generated by these 3 1 simplices, so the elements are of this form. Okay, so we can extend this definition of boundary operator to the whole of CQK by linearity. So bilinearity means we assume that this partial q, this boundary operator, is a linear function. So linear in the sense that this applied, so for example a into let's say sigma q plus b into let's say gamma q, so this is equal to a sigma q plus b boundary operator applied at gamma q. So this is what we mean by extending by linearity. So we have extended it by linearity. So after doing that, we have a boundary operator from the whole CQK to the whole of CQ minus 1K. Okay, so it is clear from the definition that this boundary operator is a homomorphism of free abelian groups. Okay, so of course it will preserve the only binary operation in CQ of K, and so that's why it's a homomorphism. So of course you can easily see it from the second condition of linearity. So the above definition says that this is sum with plus minus signs of all q minus 1 faces of this. Okay, so that's what we have done here. So if we have a 2 simplex, which is a triangle, a solid triangle in this case, then its boundary operator will give me with plus minus signs all the 1 faces. Okay, so all the 2 minus 1 faces in this case. So similarly, if you take a q simplex, then its boundary operator will give me with plus minus signs all the sums of its q minus 1 faces. Now consider this 2 simplex. We have already calculated this example. So calculate this boundary operator of K1. So in this case we have taken this to be a solid triangle. So we have already seen that how to calculate it. So it's an exercise for you to write down these outlines in a proper way. So we have an important lemma. So this says that the boundary of p pi 0, p pi 1 up to p pi q. So where pi is permutation, pi is permutation of 0, 1, 2 up to q. So this is equal to signature of pi, so partial q p naught p1 up to pq. So what are the consequences? So one of the important consequences of this is this depends only on the ordering defined by the vertices, and secondly if we reverse the order, so the sigma bar means we are reversing the order. Okay, so partial sigma bar is equal to minus the boundary of sigma. Therefore we can say that this boundary operator from this free abelian group CQK to the free abelian group CQ minus 1K is well defined. Our next result says that if I have a boundary map from CQK to CQ minus 1K and another boundary map from CQ minus 1K to CQ minus 2K, then their composition is 0. So how to show that? So the proof is relatively simple. So take any q simplex from here and apply this boundary map partial q. So from the definition we have seen that, so let's go to the definition. So the definition says that this is just equal to the boundary and with this negative sign. So just applying the definition we will get directly this. Okay, so now applying partial q minus 1. So when we apply partial q minus 1 then we can write it down in 2 stages. Okay, so the first stage is if j is equal to 0 to I minus 1, then this is minus 1 raised to power j, and there is no problem with this. So as long as we are removing the vertex before this ith vertex, so there is no problem here. But the problem arises when we remove vertices after j, because this index j is no more representing this negative sign because we have already removed this I. So it should not be minus 1 raised to power j, it should be minus 1 raised to power j minus 1, because they are not, so there is one less vertex than j over here, so it should be j minus 1. So over here, so when we are taking this case of when j is less than I, then basically these are j plus 1 vertices, okay, or we can say that before j there are j vertices, so that's why we can write minus 1 raised to power j. Okay, so now in this case, so before j they are not j vertices, they are j minus 1 vertices, because we have already removed I and we are imposing that j is equal to I plus 1 to q. Okay, so that's the difference when j is before I and when j is after I. Okay, so let me say again, so why we are imposing this condition, because according to the definition the boundary is minus 1 raised to power I when you remove xi. Okay, so when you remove xj you get minus 1 raised to power j, but when j is less than I there is no problem, we are applying the definition. But when j is greater than I, then they are not j vertices before xj, so there are j minus 1 vertices before j, because we have already removed xi. So we have already removed this xi, so they are j minus 1, so that's why we should get minus 1 raised to power j minus 1. So once again, distributing this summation, so we can write it down as minus 1 raised to power I plus j, and the same thing, and minus 1 raised to power I plus j minus 1. Okay, so these two expressions are more or less same, but the difference is I plus j and minus 1 raised to power I plus j minus 1. So if I remove this I plus j minus 1 and write down over here, so it becomes minus this thing. Okay, so now I can basically cancel out these two expressions, so these two expressions will cancel out and we will get 0. Okay, because I and j are just dummy variables. So in short, we have proved that the composition of any two consecutive boundary maps is 0. Okay, so we have this special chain, and in this special chain the elements are these free abelian groups, and these are the boundary maps, and we also have this condition. So you can see that in partial there is no subscript, so in other words it's true for any two consecutive boundary maps. So if you take these two, then this is true, and if you take the composition of these two, then this is also true. Okay, so up to so on, so there is no subscript over here, so it means that the composition of any two consecutive boundary map is 0. Such a sequence of groups is called a chain complex. So we are just taking it as an example of a chain complex. So we will study these chain complexes in detail in our future discussions. So at the moment we can just consider that this sequence of free abelian groups, and with these boundary maps and this condition, okay, is a chain complex. So with the help of chain complex, we have arrived at our final destination of today's lecture. So basically now we can define the homology group. So how to define the homology group? So given any oriented simplicial complex, we can define ZQK to be the kernel of partial Q. Okay, so CQK, CQ minus 1K, and this is the boundary map. So the kernel of this thing is basically simplicial Q cycles, so we denote it by ZQ. So ZQK lives inside CQK, and this is set of all elements whose images are 0 inside CQ minus 1K. BQK is basically the image of partial Q plus 1, so CQ plus 1K. So it says that So we have this boundary map from CQ plus 1k to CQk. So this boundary map has some image elements in this. So take elements of CQ plus 1k and the images will be elements of CQk, and we are calling them the simplicial Q boundaries, because of course we are calculating the boundary, because this is the boundary operator and we are calculating the boundaries. So that's why this is simplicial Q boundaries. Okay, so inside any Q, so let's have a look at this picture. So inside any Q we can define this homology group as ZQK quotient BQK. Okay, so in particular let's take this condition, let's take this C2 of K. Okay, so now according to the condition that the composition of any two boundary maps, any two consecutive boundary maps is 0, so this condition says that if I start from elements of C3, then I will arrive at these B2 elements, which are basically the simplicial 2 boundaries inside C2, and these B2 are the images of each and every element of C3. So take this C3 of K, and each and every element is mapped to this B2. Now this B2, as we can see from the picture, is contained in Z2. So why is that the case? Because the composition, partial composition partial is 0. Okay, in other words, partial 3 composition partial 2 is 0. So in other words, when I apply partial 3 on C3, then I get elements of C2 and we call it B2 of K. And when I apply partial 2 on these elements, so partial 2 on these elements, then these are 0, because we are saying that this is the 0 map. Okay, so this composition, so each and every element of B2 of K is going to 0. So we can say that each and every element of B2 is contained in Z2. So what is Z2? So these are this is the kernel of this partial 2. So kernel of partial 2 means set of all elements of C2 going to 0 of C1. Okay, so each and every element of Z2 is going to 0 of C1, and since this composition is 0, so the images of C3 are B2, and B2 elements of B2 must go to 0. Once again the composition is 0, so that's why this B2 must be contained in Z2. Okay, so that's why we can take this quotient. Okay, so we are in free abelian groups, and this is so ZQ is a group and BQ is also a group, and so these are abelian groups, so they are normal subgroups of each other. So B2 is normal subgroup of Z2, so we can take the quotient Z2 quotient B2. So this is called the qth homology group of the simplicial complex K. Let's calculate the homology of this simplicial complex. So this is a simplicial complex which is composed of these 1 simplices. So in other words, this is this hollow triangle. Okay, so what is the dimension of this simplex? So the dimension of K is 1. So let's go back to one of our results. So according to this result, CQ of K is 0 whenever Q is greater than the dimension of M. Okay, so which means that when we are calculating the homology of a simplicial complex which has dimension 1, then C2 of K is 0, and of course CQ of K in general is 0 whenever Q is greater than or equal to 2. So the only non-zero free abelian groups generated from these subsimplexes of K are going to be C1 of K. So what is C1 of K? So C1 of K is equal to, so there are 3 1 simplices contained in K. So let's call this sigma 1, this sigma 2, and this sigma 3. So what are the elements? A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. Okay, so where Ai's belongs to integers. And of course this is isomorphic to Z3. It's a free abelian group of rank 3. So what about C0 of K? What are the 0 simplices in this simplicial complex K? So 0 simplices are E0, E1, E2. Of course this is a very rough notation, so it means that it also contains these E1, E2, E0 as well. Okay, so this is equal to A1, okay, E0 plus, so let's call it A0, A1 E1 plus A2 E2, where Ai belongs to Z. So this is isomorphic to Z3, a free abelian group of rank 3. So so why these E0, E1, E2 must be in this simplicial complex? Because when we take the intersection of these two 1 simplices, then the intersection is E0, which must also be contained in K. So basically E0, E1, E2 must also be contained in this simplicial complex. Okay, so let's calculate our boundary maps. Okay, so what is the image? So partial 1 of E1, E2. So it is basically equal to E2 minus 1 raised to power 0 plus minus 1 raised to power 1 E1. Okay, so E1 is at the 0th place and E2 is at the 1st place. So when we remove E1, so we write down minus 1 raised to power 0, and when we remove E2, which is at the 1st place, so minus 1 raised to power 1. So basically this is equal to E2 minus E1. Similarly, what is partial 1 of E0, E2? So this is equal to E2 minus E0. Similarly, what is E0, E1? So this is equal to E1 minus E0. So now we have C1 of K going to C0 of K going to 0, and there is a 0 on its left side, and we have boundary parameter partial 1 and partial 0. So the images of this are going to be this 0 simplexes inside K. So what about the kernel of this? That's what we are interested in now. So the elements of C1 of K are combinations. So A sigma 1 plus B sigma 2 plus C sigma 3. Okay, so partial 1 of this is equal to A partial 1 of sigma 1 plus B partial 1 of sigma 2 plus C partial 1 of sigma 3. So which is equal to A into, so what is partial 1 of sigma 1? So sigma 1 is E1, E2, so this is E2 minus E1, E2 minus E1, plus B sigma 2 is E0, E2, so which is E2 minus E0, plus C sigma partial 1 of sigma 3 is E0, E1, E0, E1, so E1 minus E0. Okay, so now combining, so what are the coefficients of E0? Minus B and minus C, so these are the coefficients of E0, plus what are the coefficients of E1? so minus A and plus C plus, so what are the coefficients of E2? So A plus B. Okay, so now this is 0 if and only if B minus C is 0, minus A plus C is 0, and A plus B is 0. So in other words, so we have the following conditions. Okay, so let's see what are the conditions. So B is equal to minus C, A is equal to C, B is equal to minus A. So basically each and every one can be written in terms of, for example, C. So B is equal to minus C, A is equal to C, and of course C is equal to C. So what are the elements going to 0? So these are going to be C sigma 1 minus sigma 2, so plus minus C into sigma 2, and so C remains C sigma 3. Okay, so which means that sigma 1 minus sigma 2 plus sigma 3. So basically the elements of C1 of k going to 0 are basically multiples of sigma 1 minus sigma 2 plus sigma 3, or in other words the Z. Okay, so let's go back to the definition of Z. So basically this is the kernel of this. Okay, so Z1 of k is basically a free abelian group generated by this one element. Okay, and so it is isomorphic to Z. It's a free abelian group of rank 1. So what about our first homology group? So H1 of k is equal to, let's have a look at the definition. So it says that so the elements going to 0 and the elements which are the images. Okay, so the boundaries. So partial 2, it's coming from 0 to C1 of k, and since it's a homomorphism, so the image of 0 under homomorphism is 0. So B1 of k is basically just identity. So when we take quotient of okay, so when we take quotient of Z1 of k with B1 of k, then okay, so Z1 of k quotient with B1 of k, so basically we are taking quotient of this free abelian group of rank 1 with the identity. So basically this is isomorphic to Z. So H1 of k is isomorphic to Z. Now let's see how to calculate H naught of k. So in this case basically the elements of C naught of k which are going to 0 is the whole of C naught of k, and you can easily calculate that what are going to be the boundaries inside C naught of k, and you can easily see that this is going to be Z naught of k quotient with B naught of k, and what is B naught of k and what is Z naught of k, you can easily calculate it using the same procedure. Now let's consider another example of surface of tetrahedron. Okay, so a surface of tetrahedron as a simplicial complex, of course it will contain other elements as well. So this is rough description. So we consider this surface of tetrahedron as a simplicial complex. Okay, so we can calculate the simplicial homology of this simplicial complex. Okay, so of course in this case we will be having C2 of k and C3 of k, and higher will be 0, and similarly we will have C1 of k and C naught of k, and this goes to 0. So this is the boundary map partial 2, boundary map partial 1, and the boundary map partial naught. So this is the free abelian group generated from the two simplices inside k. So what are the two simplices inside k? So 1, 2, 3, 4. So there are two simplices inside k, so it's a free abelian group of rank 4. Similarly C1 of k is the free abelian group generated by 1 simplices. Okay, so how many 1 simplices are there? So 1, 2, 3, 4, 5, 6. So 6, so it's a free abelian group of rank 6. Similarly, we can calculate C naught of k up to so on, and then we can easily calculate the boundaries. Okay, so we can calculate partial 2 of any 2 simplex inside this, and after calculating the images of each and every 2 simplices, so there are 4 of them, so after calculating these images, then we will do the same operation. So for example, this is sigma 1, this is sigma 2, this is sigma 3, this is sigma 4. Then we want to calculate such that, so the elements A sigma 1 plus B sigma 2 plus C sigma 3 plus D sigma 4. Okay, so such that this is going to 0. Okay, of course this is a linear operator, so this is equal to this, so B partial 2 sigma 2 plus C partial 2 sigma 3 plus D partial 2 sigma 4 equal to 0. So we have already calculated this thing. Of course you can easily calculate these things. So after putting its value and following the same procedure as we did in the last example, we will see that we can calculate the kernel of partial 2, and similarly the kernel of partial 1, kernel of partial naught, up to so on. And similarly we can calculate the boundaries, so the image of partial 2, image of partial 1, and the image of partial naught. Okay, so after calculating all of these things, we can easily calculate the simplicial homology groups. So I'm leaving this as an exercise for you. So next time we will continue our discussion of the simplicial homology. This is the end of the lecture. Thank you very much, and Allah Hafiz.